this part, we are going to take a look at the segment registers. Okay, so segments are specific areas defined in a program for containing data, code, and stack. There are three main segments. Okay, so we have the code segment. Okay, and the code segment, this one contains all the instructions to be executed. Okay, and a 16-bit code segment register, or the CS register, stores the starting address of the code segment. Okay, so from there we have the data segment. Okay, and this one contains the data, constants, and work areas. Okay, so a 16-bit data segment register of the DS register stores the starting address of the data segment. Okay, so we have another segment which is called the stack segment. Okay, and this one contains data and return addresses of procedures or subroutines. Okay, and it is implemented as a stack data structure. Okay, and the stack segment register, or the SS register, stores the starting address of the stack. Okay, so let us take a look at all these ones that we. So inside here, inside the GNU Nano editor, I have a file called the register underscore example.asm. Okay, it's an assembly file. Okay, and this is what we have inside. I'm going to explain everything. I'm going to explain what it does. So here, let me create a comment. Okay, so here we talked about the code segment. Okay, and the code segment contains all the instructions to be executed. Okay, and a 16-bit code segment register called the CS register stores the starting address of the code segment. Okay, so we have another one that we talked about, the data segment. Okay, and this one contains data, constants, and work areas. And the 16-bit data segment register of the DS register stores the starting address of the data segment. Okay, so here we talked about the DS register. Okay, so from there we have another one which is called the stack segment, and this one contains data and return addresses of procedures or subroutines. Okay, and it is implemented as a stack data structure. Okay, so for example here, the stack segment register, or the SS register, stores the starting address of the stack. Okay, as we said before. Okay, so apart from the DS, CS, and the SS registers, there are other extra segment registers. Okay, so for example, we can talk about that as the ES. Okay, the ES extra segment. Okay, and we also have the FS, and also we have the GS. Okay, which provides additional segments for storing data. Okay, so we shall take a look at these ones later. So this is also a comment. Okay, it's also a comment like that. Okay, so in assembly programming, a program needs to access the memory locations, and all memory locations within a segment are relative to the starting address of a segment. Okay, and the segment begins in an address evenly a segment begins in an address evenly disabled by the 16 or a hexadecimal 10. Okay, so all the rightmost hex digit in all such memory addresses is 0, which is not generally stored in the segment registers. Okay, so the segment register stores the starting addresses of a segment, and to get the exact location of data or instruction within a segment, an offset value or a displacement is required. Okay, and to reference any memory location in a segment, the processor combines the segment address in the segment register with the offset value of the location. Okay, so I think you have understood. So let us take a look at the example we have right here. Okay, which uses registers. Okay, in assembly, and this program displays 9 stars on the screen along with a simple message. Okay, so let us take a look at it. Let us translate everything. Okay, So here we have the section called the .text. So this is the text section, okay, and under the text section we have this keyword global main, okay, global main, and this is required. This is required for the linker, okay, which is the GCC compiler, okay. And from there we have our main label, okay. So we have our main label, and this one tells our linker the entry point, okay. So from there we start using these registers, okay. So we start by moving the length of a certain message, which we defined right down here. Right down here we shall talk about the data section, but let us start here by translating what we are doing right here. So here we start by moving the length, okay, the length or the reference to the length of our message into EDX, okay, into EDX, and this is the message length, okay, the length, okay, it's the message length, okay. So from there we move the MSG, which is our message, into ECX, okay. So here we provide ECX, the message that we are going to write, okay, that we are going to write. From there we move one into EBX, okay, move one into EBX, and this is one is a file descriptor, which is the standard output, okay, the standard out, std out, okay. So from there we move 4 into EAX, okay, and this one is called 4 is called the system call number, which is known as the syswrite, okay, the syswrite for writing, okay. So from there we call our kernel, okay, we call our kernel using int 0x int, okay. So we can as well use int h, okay, like that. We can use int h, okay. So from there we go down here. So from there we perform some other instructions, and here we move 9 into EDX, okay, and 9 it's the length, okay, it's the length of it's the message length, and from there we move S2 into the ECX, okay, and S2 is the message that we want to write, okay, and from there we move 1 into EBX, okay, move 1 into EBX, and 1 is a file descriptor, which is known as the standard out, std out, okay. So from there we move 4 into EBX, okay. So whenever we want, so this 4 is used for what? Is used for writing, okay, and it's the system call number, okay. So whenever you want to write a message on the screen, you have to move the length of the message into EDX, okay, EDX, and then you move the message, okay, into ECX, or the reference to the message into ECX register, and then you need to provide EBX must have the file descriptor, which is 1, and then EX must have a system call number for writing, okay, which is the syswrite for writing, and then you must call the kernel, okay. So from there, let us take a look at this one here, right here. So here we are moving EX, we are moving 1 into EX, okay. So this is called 1. When we move 1 is called the system call number. This is a system call number, and it's for exiting, okay. So it's sys exit, okay, for exiting, okay. So from there we call our kernel. We call our kernel using int 0x8, like that, okay. So from there we go down here, and we define our section, our data section, as you can see, section dot data, okay. So from there, as you can see, we have our MS key, and we are storing bytes, okay, and these are the bytes that we are storing, displaying nine stars, okay, and then we move the cursor to the next line, or we break the line, okay. So from there, this becomes our entire message. From there we need to determine the length of our message, and then we use the equal keyword, then $sign dash, okay, $dash, okay, to determine. So this one helps us to determine the length, okay, the length of our message, okay, and then we provide the name there, right there, okay. So from there from there we are going to print 9 stars. Okay, and in order to do that, instead of repeating 9 stars like we have done here, okay, instead of writing the entire 9 stars, okay, we are going to use the times keyword. Okay, so we use s2. Okay, we are going to name our stars. Okay, so as s2. Okay, s2, and then we are going to, so this s2 is going to give us access to these 9 stars. Okay, so times, we use the times keyword, we are going to multiply those stars. So these stars, they are like, it contains like 1 byte. Okay, 1 byte of memory. Okay, so 1 times 9. Okay, so times 9, so we are storing bytes. Okay, and then we are multiplying by 9. Okay, by 9. So from there, if we try to save, okay, press Ctrl S to save, and then Ctrl X to exit, we are going to start compiling. Let me use clear, okay, to clear my screen. Okay, so from there we have our file called the register underscore example.asm. So we need to call our assembly, we need to call our assembler nasim, and then dash f, elf, and then elf, and then the name of our file. It's called register underscore example dot asm, like that. Okay, so after assembling, we are going to generate a O file. So if I type dr or ls, like that, as you can see, we have register underscore example dot o. Okay, we have our object file there, and we have to link, we link using ld binary. So ld dash m, and then elf underscore i386. Okay, from there we use dash s dash o. So it's going to be, the output is going to be called register underscore example, and then our file is called register underscore example dot o, like that. Press enter. As you can see, so here, don't mind about this error. If you watched my previous parts, you should be knowing why this error has been thrown. Okay, so from there, if we type ls, as you can see, we have generated our file that we can execute. Okay, so from there, let us execute using dot forward slash register underscore example, like that. Okay, so because it's the name of this executable file. Okay, so from there we can press enter. As you can see, displaying 9 stars, our message that we had, and then our 9 stars, 1 2 3 4 5 6 7 8 and 9, like that. Okay, so that is it. That's how we use registers. Okay, so we shall take a look at how we can use all these other registers. Okay, or other segment registers. Okay, in future parts. Okay, so thank you if you have liked the video and you have left a comment. Okay.